So okay, I have started the recording now. So I'll share the screen. I hope like you guys are able to see it. Can someone confirm? Maybe in the chat you can write if someone. Okay, so I hope like you are able to see my screen. Now, so this is the like week 2 session of NPTEL CS52 reinforcement learning by Professor Balaraman Ravindran. But he's from CSC IIT Madras, and I am a PMRF scholar, Prime Minister Research Fellowship. And basically, like we have to cover like 25 hours of teaching every semester. So like there are 12 weeks in this course. So I'll be taking 2 hour session every week. And at the end, like after just before your exams, like we'll have one bonus session of 1 hour. So that will make it 25. So I'll repeat the details again. Like maybe some of the people might be joining for the first time. So like basically like there are three parallel sessions going on. So first is on Saturday, second is on Monday, and third is on Tuesday. So this is the one on Tuesday, and the link for attending this session is given here. I think the Monday one is on Google Meet, other two are on Microsoft Teams. And who can attend is anyone who has taken this CS 52 RL course, they can attend. And why to attend? Like there will be discussion on problem solving and doubt clarification, also discussion on practice assignments and assignments. So for assignments, I won't be giving you exact answers because deadline is still there. So I'll be like guiding you towards the answer. The answer you will have to deduce it yourself. And one of the biggest reason to join these sessions is two-way communication. So basically for like your main content, like you are given recorded lectures, but there is no component of two-way communication. So you cannot like ask your doubts and all. So for that, like these sessions are being conducted. So the expectations again is that you have to watch the videos, weekly lecture videos. So this is the session for week 2. So you should have watched all the like 6 videos of week 2 and at least made an honest attempt on weekly assignments and practice assignments. And it is recommended to read the Satin and Bartok book. Although like I know like many people won't get time, but try to get some time and read the book. It will help you in the long run. And the slides of this session and the recordings again will be made available on the same Google Sheet, like which on which we shared it last week. So guidelines are the same, like just keep yourself muted to avoid any background noise. You can ask the doubt in chat or just unmute yourself and ask at that point. And the thing is like try to be responsive and try to solve the problem simultaneously. So today's session, like there is a lot of problem solving. Like you'll need to do some calculations. So keep your calculator with you and I'll be giving time to solve when required. So the order of the session is again the same as last week. We will first discuss the practice assignment, then do some problem solving. So these problems are different from your practice assignment and assignment. And in between, like we will do a demo also. So this demo will be in Python. I'll be sharing some code on UCB algorithm. Okay, so like maybe audience interaction. Is there like someone who is new in this meeting? Like who has joined for the first time? I can see like Harshit. Yeah, maybe you can introduce yourself. Like what course, like why do you want to take this course, and what is your highest like qualification, educational qualification, like bachelor's or master's?
So I am currently in the eighth semester. So
Yeah,
as my college allows for like doing internship in the last semester, so I opt for this course in
okay,
lieu of like the regular semester courses.
right, right. So you are from which college?
JP Institute of Information Technology.
Right, right. So I think Jaya Balan, she gave introduction last week also. So there's another
Okay.
person 2350 external. Can you introduce yourself?
Sir, I am Lakshmi Narayana
Mm-hmm.
from Gates
Like
College, sir.
right.
Yes, sir.
And you are bachelor's student or master's?
I am a BTech student, sir. Final year.
Right. Okay, okay, got it. So today, like, there are like very less people. So either way, like, I have to ask this information in every session because some people join on some session and they won't be there in the next session. Okay, so like, is there something like some kind of feedback? You might have watched the recorded video of last week. So is there some feedback for me which I can incorporate from the next lectures?
So can we get slides that the teacher is teaching from?
Yeah, yeah. So
Yeah, exact
teacher,
same slides.
okay,
Yes.
teacher slides.
Yes.
Like teacher is teaching on board, right?
No, like in the first week, like in 2 to 3 lectures, teacher has taught from like some slides. So, or maybe some notes like that because transcripts are like too long to read. So,
Mhm. I think like the idea is that you will be watching these recorded lectures and you will be preparing your own notes. So
okay.
I think that is the idea. That's why they haven't provided any notes. Either way, like
Yes, yes.
I haven't.
I am
Yeah,
I am making my own notes, but like if someone has already created or like if someone has like notes from like which like someone has taken the course in the previous year and
right, right.
has notes about that, so that will be like helping for me. That's why.
Okay, so I'll try to find this out if like it's available, but I'm not sure whether like even if they are available, whether they will allow to share because like the idea
Okay.
here is that you make your own notes. Whereas like
Yes.
generally like the when people make notes, they make notes of only those things which they don't know. Like whatever is already in their mind, they won't make. So that differs from person to person. So maybe
Yes.
like
Yes.
some notes will be rigorous, or maybe some person might write very little. So that thing varies. So I'm not sure. Like basically, like you should focus on making your own notes, and I'll
Okay.
see if it's possible.
Okay. Okay. Sure. Sir. And sir, which book should I follow?
Yeah. So book is like this Sutton and Bartow book. Like it's the standard reinforcement learning book. So second edition came in I think 2020. It's available online, so you can download it. It's called Reinforcement Learning by Sutton and Bartow. So these are like known, like basically these are the guys who kind of popularized reinforcement learning. So these are the main authors. So I'll maybe share the link of the book, right?
Okay. Okay.
Okay, so these are the like week two topics. Like there is UCB1 concentration bounds, UCB1 theorem, then there is Peck bounds, and after that we like discussed median elimination and at last Thompson sampling. Okay, so let's begin with the practice assignment. So like which of the following is true of the UCB algorithm? So is the like action with highest Q value is chosen at every iteration? Like if like we choose the action with highest Q value, just the Q value, basically the expected reward. Like, do we choose that way or there is some extra term, right? There is this extra term Q current plus 2 ln of n upon whatever r. So this is for I. So this extra term is there. So basically like this is not true, right? After a very large number of iterations, the confidence intervals of unselected actions, a key term is unselected actions, will not change much. So if like some action is not selected, so basically the only way it can vary, like this will remain same because it is unselected. This will also remain same because it is unselected, but the term which will vary is ln of n, which is the like total number of poles of any arm. So this will like keep on increasing. So, but we know that log like the graph of log like is this. So maybe I'll mention some values. Suppose ln of like this is 1 lakh maybe. So 1 lakh is equals to 11.5129. Now if we increase this to by 1, then again it remains like this 11.5129. 2.5129. And if we keep on increasing by this, the only place at which this will change is when we do like when we reach 8, and it will also again changes 513 third decimal place. So the change is quite minimal, right? You can see that. And again, on top of that, there is one square root also. So this will also diminish that effect. So after a very large number of iterations, like the confidence intervals of unselected actions will not change much. So this is true. Now the third option is the true expected value of an action always lies within its estimated confidence interval. Like this always is the issue. Like it might go beyond the confidence interval also, right? So this is again not correct. And with a small probability epsilon, we select a random action to ensure adequate exploration of action space. So this happens in epsilon greedy algorithm, not in UCV. In UCV, like the exploration and exploitation is handled by this bound term. And I'll demonstrate it in the demo, like this, how this exploration and exploitation happens. So I hope like this question is clear to every one of you. Okay, if there is no more doubt, like I'll move to question 2. So this is like a solving question. So you'll have to like solve it. So in a 4-arm bandit problem, so the value of k is given to be 4. And after executing 100 iterations of the UCV algorithm, so our n is 100. The estimate of q values are like they have given the q value estimates of all 4 arms after 100 iterations. And the number of times these arms have been sampled is also given. So which arm will be sampled in the next file? So in UCB algorithm, we just have to find the UCB values of all the 4 arms and see like which one will have the highest UCB value, and then we will pick that arm, right? So has anyone like tried this before? Maybe I'll check chat once. Okay, so there's no response. So maybe like I'll help you solve this. So let's take R number. So the estimate of Q value is given to be 1.73. Now what we need to add to it is this bound. This will be 2 of ln of 100. And how many times this arm has been pulled? Upon 25. So basically like you have to solve this value and get one value. So maybe like I'll solve this 1.73, and then this will be like ln 100 is almost 4.6. So 2 into 4.6 upon 25. Now this term will become 1.73. This remains the same. Square root of 9.2 upon 25. And this is equals to 0.368. Now when we take the square root, it becomes 1.73 plus 0.6 approximately. And when we add it, it becomes 2.33. So the estimate for arm 1 is 2.33, right? In a similar way, we can calculate the estimate of arm 2 also. So for arm 2, like the Q value is given to be 1.83. And now we again have to add. So this numerator remains same, right? So it will be 9.2 only, but the arm 2 has been sampled 20 times. So again, like we will solve this. So it will become 1.83 plus, and this square root term will be like when you take the square root also, like it will come out to be 1.83 plus 0.68, and this will be 2.51. So the estimate of UCB value for arm 2 is 2.51. So now let's see for arm 3. So for arm 3, the estimate given is Q value estimate is 1.89, right? And again, like we will be doing this. This term remains the same, 9.2. But arm 3 like has been sampled how many times? It is sampled 30 times. So again, like in a similar manner, you can calculate this. This will come out to be 1.89 plus 0.55, and this will be 2.4. So again, like we have the estimate for arm 3 also. So for arm 3, like the estimate is 2.44. Now we do the same calculation for arm 4. So arm 4 estimate is given to be 1.55. This is Q value estimate. We calculate the confidence interval. Again, numerator remains same, but the number of times arm 4 has been sampled is 15. Again, you calculate this, so this will come out to be 1.55 plus 0.78. And this will be again 2.33, same as first arm. So these are like approximate answers. So the Q, this UCB estimate for all the arms, we have it. So which one has the highest? It's arm 2. So arm 2 is the answer.
So,
So yeah,
sir, first one should be 2.34 after rounding off. Like we are
yeah,
getting
yeah. So
2.369 something.
that approximation you can take care of. Like the difference is quite high. Like 2.51 is quite far away from 2.33. So
Yes, yes.
yeah, so that the calculation like I have done it till like two decimal place. You can like try more and round it off to get more accurate estimate.
Okay,
So
okay.
basically
So
the
like
thing is
we,
like, yeah, tell me.
so sir, like we will get virtual calculator in the examination, or like we have to take hours.
Uh, I'm not sure about exams because I haven't taken NPTEL exams, but
Okay.
I think like either they will allow the calculator or they
Mhm.
will allow log tables or something, or maybe they will mention the value of ln 100.
Okay, okay.
And so this is like something which is like repetitive. You are not expected to know the value of ln. This could be something
Mhm.
else also, right? Apart from 100.
Yes.
So, or either like they will put it like e raised to power something so that you can solve, right? So that will be done like, but that comes at a very later part. You'll be given proper instructions for that.
Okay, got it.
Right. So now we move to like question number 3. So question number 3 says like it's a assertion and reason type of question. The confidence bound of, this is the key term, each arm. Each arm in the UCB algorithm cannot increase with equations. Like if we are not selecting some arm, then like for that arm, like it will increase, right? Because like UCB estimate is like Q current estimate of ith arm plus root 2 times ln of I. So like if we are not selecting, then this remains same. This also will remain same because we are not selecting that arm. But this n is always increasing. Either if you sample like some other arm also, so the total number of times an arm has been sampled, this will keep on changing. And so it will increase for the unselected arms, right? So this point that it cannot increase for each arm is wrong. So assertion is definitely false. And the reason for this in like the assertion itself is false, and the reason they have given it, the nj term in the denominator ensures that confidence form. So I have used I, they have used j, that doesn't matter much. The nj term in the denominator ensures that the confidence bound remains the same for unselected arms and decreases for selected arm. It doesn't remain same for unselected arms, it actually increases. So this reason is also false. So like our answer will be both assertion and reason are false. So is there like any doubt in this? I think this is pretty easy. Maybe I'll check the chat once. There is anything there. Okay, so there's nothing. So I'll move to last question. Again, like this is like directly from the proof of UCB algorithm. Like those people like who have watched the like that video of UCB algorithm theorem, they can do it simply, like just by reading the options. So there are like four, either two equalities are there and two inequalities are there. And the notation used is same as the lectures. It's just that we have to point out like which of the equalities or inequalities are correct. So TIN, like it represents the number of times that action I has been played in the previous n trials. Okay. So this we can write like second option. This is straightforward. This means that this is an indicator function. So this means that if like the condition inside these braces is true, then it will be 1. Otherwise, it will be 0. So like we are basically summing up from 1 to n, and we are checking whether like the arm pull at m step was this arm I or not. So this will basically return the same thing, right? So this is correct. And secondly, like they have basically what they have done is they have sampled each arm once beforehand. And so this one comes for ith arm also. And from m equal to k plus 1, there are k arms. They are counting till n and again checking this indicator value. So again, like this will also return the same thing. Now, third condition is this, that this quantity Ti of n is lesser than 1 plus this summation m is equals to k plus 1. And this is the, so basically like when does this condition happen? That you will pull an arm I. You will pull an arm I when like this is the Q, like UCV value, this these two terms combined. So you will pull an arm I only if like it's like greater than the optimal arm. So like this is like a slightly like not that rigorous condition. That's why like this lesser than or equal to comes into the picture. So again, like if you have watched the lecture of the proof, you will know that this is correct. And in the same way, like you can derive like fourth condition from the third condition. So this basically means is that if A plus some positive quantity is lesser than equal to B, then A will definitely be lesser than or equal to B, because we are like kind of removing this positive quantity. So again, like this is also correct. So the correct options are 1, 2, 3, and 4. So this is the answer. So is there like any query, like we are at the end of section of problem, like this practice assignment. If there is any query in any of the question, you can ask me now. Maybe I'll check the chat again. So there is no query till now. Okay, then like I'll move to problem solving. So in this section, like I'll be discussing some problems which aren't part of your practice assignment and assignment. So this will help you prepare for the upcoming exams. So the question one is in the UCB1 algorithm. So yes, even the professor told that there are many variants of UCB, like UCB revisited, UCB improved. Even there is one more called KLUCB. You can read about them if you are interested. So this question focuses on UCB1 algorithm. How is it ensured that the confidence bounds around the estimated values for each arm shrink? So basically, like we want that confidence bound should shrink, right? So like how does the UCB ensures this? So first thing is the intervals do not shrink. Like this is wrong, right? Intervals actually shrink for the selected arm. And the confidence interval of each arm are made to shrink after every arm selection. Like here is the point. Like do they shrink for each arm? I don't think like they don't shrink for each arm. They shrink only for the selected arms, right? So for unselected, it actually grows the bound with log. So this we have seen before also. So again, like this each is causing trouble here. So third option is in calculating the amounts, we use the number of times an arm is selected in the denominator. So this will actually like help, right, in shrinking that if an arm is selected. And so it is basically growing by ln of n, and this denominator, like it increases by 1. So like this is like kind of shrinking factor. And on selecting an arm, its interval is shrunk by half. Like it need not be necessarily shrunk by half. It shrinks by this, and there is that under root. So basically, like you have to like calculate the confidence bounds at 2 consecutive steps and see like how it shrinks by subtracting the previous one from the new one. So it need not be half. So this is again wrong. So the correct answer is C. Is there any doubt in this? I hope not, because like this is quite simple. I'll check the chat. No, so there is no doubt. So now we move to second question. So for the first question, like I solved it. Like this question is for practice. So one more thing I want to point out, like in this second question, there is an error in the question itself. Can someone point it out to me? Does anyone notice there is an error? Although like we solved it with the given values, but there is an error in this question. Like maybe you can write in chat if anyone of you have noticed that error. Yeah, right. So Jaya Valan says that it's not 100, it's actually 90. So this is a mistake like by the person who made this assignment. So actually like there are 4 arms, and they have mentioned that it has been sampled 100 times, these arms. And but this like these four quantities, like they sum to 90 only, 25 plus 20, 30 and 15. So it's 45 and 45 again here, 90. Not sure how they missed this, but this is the issue. So after 12 equations, so here like we can see like 4 plus 3, 7 plus 2, 9 and 3, 12. So this is like perfect here. So again, like after 12 equations, they have given the estimates of all 4 arms. So again, the question is like which arm should be played next? So the same exercise like needs to be repeated again. Like you need to calculate the UCV values of all the 4 arms and see like which one has the highest value of UCV. So like maybe I'll give you like guys 2 minutes and you can try to solve this. Like let's see who gets the answer first in the chat. Because this question is like you guys have not seen this question before. So maybe you can try simultaneously. I'll write also. So for 1 arm, it will be like 0.55 plus under root of 2 ln of 12, and first arm has been pulled 3 times. This is for arm 1. For arm 2, we will have 0.63 plus under root 2 ln 12. This numerator remains same, and arm 2 has been pulled 4 times. And for third arm, it will be 0.61 plus root 2 ln 12 upon arm 3 has been pulled 3 times. And for arm 4, it will be 0.40 plus 2 ln 12 upon 2. So you basically have to solve these and like see which one has the highest value. One more thing, like I'll mention it in this question. As you can see here, like even though like the expected value was highest for arm 3, it was 1.89, right? Still like arm 2 was pulled. This happened because like due to that confidence bound. So that confidence bound changes things. So it kind of balances between exploitation and exploration. How this does is because like if some arm is not selected for a long time, then it's like denominator will remain same, but this numerator term will keep on increasing. And once it has increased sufficiently, then it will overtake this Q values. So this bound will kind of affect that. So even though like ARM 3 had the best Q value estimate, but like UCB estimate of ARM 2 was better. So again, like, I'll check in chat if someone has got the answer. If you want like 2 more minutes, you just need to like do the calculations and get the answer. I hope like you guys have some calculator, scientific or even a physical one with you. This so meanwhile, like I have solved them before, so I'll write the values. For ARM1, it will come out to be 1.837. For ARM2, it will come out to be 1.745. For ARM3, it will come out to be 1.897. And for ARM4, like it will come out to be 1.976. So again, like fourth arm has the best UCV value, so it will be picked in the next result. But I hope like that you guys actually solve this, because like these might be there in the exams. Then you have to practice, because like you need to solve these within times. Maybe they will supply the ln values, but you need to perform this square root and all the calculations. So this is like again a simple question. Like this is based on like the same lecture UCV theorem derivation. So this, I won't mention the answer. I'm expecting the answer from you. So there is an expression given, like this is inside the same indicator function. The question is, what does this expression stand for? So basically, like, what does this expression represent? So let's see, like, who writes the answer in chat? Is it option A, option B, option C, or option D? Maybe you can take a minute to read all the options. Again, like for question number 2, like Jayabalan wrote the answers for 3 arms correctly. So again, another question is, which course is it? Programming in C? No, this is like reinforcement learning course. So like which one is it? Like is it A, B, C, or D? So you can figure it out from these min max operators also. What does it represent? At least take a guess. Okay, then maybe I'll explain. Like basically, like the answer here is B. So it represents like the minimum value among the. This is the UCB value, right? This is the Q value estimate, and this is the bound C. So minimum value among the UCB bounds of an optimal arm. A star denotes the optimal arm, right? Till the mth step. So we are like calculating, like taking this min over from 0 to m, and both are not included. So it's essentially from 1 to m-1. Up till mth time step is less than or equal to, yeah, to the maximum again value among the, this is the UCB bound, UCB value for ith arm, right? And this is from between time steps L to M. This was like pretty straightforward. You guys might be asked these questions, so like it's required that you have to go through those derivations. Like generally, I've seen a tendency that people skip the proofs, but they are important. Okay, let's move to the next question. I hope like this is clear, right? It's just a copy paste from the lecture itself. So those who have watched the lecture, they can simply answer it. So in the initial stage of UCB1 algorithm, each arm is selected one time. Yeah, this is correct. Do you know like why this is done? This is done because like UCB is value is this, right? 2 of ln n upon ni. So this thing will be 0, right? This will make the entire quantity undefined. So first we sample it at least all the arms at least once so that this UCB value becomes at least defined. Otherwise we will be dividing by 0. So due to this, we do this initialization. This Q value, like we can initialize it to 0 maybe, but this confidence bound causes issue because this denominator has an I. So thereafter, the arm that is selected depends on the arms with the maximum upper confidence bound. This is also correct. So suppose that one of the arms has not been selected after its initial selection. So it has been selected in the like this when we are selecting each arm once, but after that it hasn't been selected. What happens to the upper confidence bound of this arm? So basically what they are saying is this has been sampled once. So this value denominator is 1. Q maybe something, we can call it maybe some C. But again, like this is after first sampling and it hasn't changed after that because it hasn't been sampled. But this due to this numerator, like this will keep on increasing, right? So the confidence upper UCB of this arm will increase of the unselected arms. Right? I hope you agree with this. So yeah, like if there is no more doubt, like I'll move to the next question. So this is regarding the naive pack algorithm, which was discussed in the class, and k equals to 10, number of arms equal to 10. So suppose that we apply naive pack algorithm on 10 arm bandit problem where they have given the value of epsilon as 0.5 and delta as 0.05. So basically like you are supplied these values and you are asked this, how many iterations would the algorithm take to output n arm selections? So iterations basically mean how many times you have to sample like the arms. So like there is a phase in which we are looping over arms. Like for each arms, we will sample this many times. And then at the end, like we will output the arm with the highest Q value estimate. So this is the naive pack algorithm. So the question which they have asked is how many iterations would the algorithm take to output an arm selection? So again, like for each arm, we are like doing it how many times? So it's let's calculate for one arm. So 2 upon 0.5, we can write it 1 by 2 square ln of 2 is 10 and delta they have given 2 is 0.05. We can write it like 5 by 100. So this becomes like 8 ln of 400. And this comes out to be around 47.93, right? But we can approximate it to be almost 48. So what should be the answer? Is it 48 or something else? You can write in chat. Take your time. Think about it. Is the answer 48 or something else? The point to consider is this. This is for one arm, right? And they have asked how many iterations would the algorithm take to output an arm selection, basically to output the best arm. So basically, like we have done this for one arm, but we need to repeat this exercise for all 10 arms, right? Then only we will be sure like which arm has the best value. So we will be sampling it actually 10 into 48, which is 480. But like again, like you need to be careful. Like this 48 is mentioned here. So many people when they see the option 48, they will simply get excited and tick it. But this is the point where many students make a mistake. So you have to be careful here. Okay. So like we have covered 5 questions in problem solving. If there is any doubt in any of those 5, like you can ask in chat. We'll check chat once. So there is no doubt till now. I think the questions are fairly simple, and if anyone has seen the videos, they can simply do it. Just some calculation is required. So now we move to the next question, which is the 6th question. And it says in the, again, like this is for naive pack algorithm. So in the proof of naive pack algorithm, we had this expression in which we wrote that some arm A dash is there, which is again not optimal arm. And the probability that its Q value estimate is greater than Q value estimate of like the actual optimal arm. This probability is lesser than or equal to probability of Q of like this one plus epsilon by 2 or this one. So the question which they are asking is why is the LHS less than or equal to RHS there here? So maybe like I'll give you an example. So this will help you understand better. So suppose if write a statement that Earth's atmosphere comprises of 78% nitrogen, 21% oxygen, and 0.03% carbon dioxide. So this is suppose our left hand side. And on right hand side, we write 2 statements that Earth's atmosphere comprises 78% nitrogen. So again, like second statement is and 21% oxygen. So there are like 2 statements and we need to see. Basically, like the idea here is this that so on the left hand side, we have like some strict condition on CO2. But on right hand side, we haven't like restricted it to have any value, right? It can take any of the value. So the right hand side is slightly bigger event compared to left hand side. So we can apply the similar analogy here. So like basically the thing is like this condition inside the probability. This implies the conditions inside this probability. But it is not true in the reverse way because there is some extra factor here. More, something more can be here. So this like event on the right hand side is like kind of superset of the event on the left hand side. So again, like when we represent in terms of probability, the left hand side will have lesser probability and this will have more probability. So the correct answer here will be because the occurrence of at least one of the events on the RHS is a necessary. So this will imply like this one, right? So you can see from here, LHS will imply like first statement of RHS like this. If we name it one, this is, it will imply one also. RHS, like LHS will imply statement two also. But if we combine like LHS, like RHS's both statements, do they imply like LHS? No, they won't because you need an extra condition on this one. So second one, like RHS is bigger event because it can take different values of this. So in that way, you can think like this. So because the occurrence of at least one of the events on RHS is a necessary, so this will imply this, but reverse is not possible. So this necessary and sufficient, I hope you know this. So if there is no more doubt, I'll move to next question. I'll check in chat. There is no doubt. So let's move to question number 7. So here, like suppose we have a 64 arm bandit problem. So K is equals to 64. So this question is pertaining to median elimination algorithm. And they have given epsilon value also, delta also. How many times do we sample arms in the first round? So, and they have also given the formula also. So it's just simple calculation. But the point to note again is they have asked for arms, not each arm. So keep that thing in mind, which happened in this question, like where 48 was also given and 480 was also given. So again, like we just have to plug in the values. So so basically, like you have to calculate the these values epsilon L. So epsilon L in median elimination algorithm. So this is asked that first round, right? So first round we need to calculate epsilon 1. For the median elimination algorithm for first round, it's epsilon by 4, right? So it's already half, so it becomes 1 by 2 raised to power 3, 1 by 8, right? And delta they have given 1 upon 100. Now in the median elimination algorithm, delta 1 is delta by 2. So this becomes 0.01 by 2. You can write it like 1 upon 200. So the question now, like once we have got the value of epsilon 1, delta 1, we just simply need to plug those values here and again like do the calculation, right? So it will become, so again like this denominator I'm taking to numerator 2 and this will be in denominator. So again it will go up. So into 2 raised to power 3. Right? And one more thing, like I forgot this. This is squared, right? So when we take it to numerator, it will become squared. So it will be 2 into 2 raised to power 6. Now we take the term ln 3 will remain the same and delta L. So it's like we go up and multiply 200. So it's essentially like this term is 128 ln 600, right? And when you solve this, it will come out to be around like this ln term will be around 6.39 and this entire term will come out to be 818 0.8, which we can approximate to 819. Now, once we have approximated it to 819, like this we have calculated for one arm. Again, like there are 64 arms here. So you need to multiply this number by 64, 64 into 819. And this will come out to be 52416. Right? So this is actually the answer C. But although like I am doing these calculations here, I'm expecting you to do these calculations. Like I'll be sharing slides both annotated also without annotation. So you should practice these examples. Now again, like this is a like continuation of previous example. What is the number of samples in the third round? This is the key point. Like in last question, like we asked in first round. So this in third round. So basically, like we'll have to calculate the value of epsilon and epsilon delta at third step. So this will be like some kind of like what was the previous value of epsilon? It was like 1/2, right? And epsilon 1 like becomes epsilon by 4. So it's already like 1/2, and it became multiplied by 1/4, and this is after the first round. So like in two more rounds we will be multiplying it by 3/4. This will happen twice. So this basically can be written as 3 square 2 raised to power 4, 2 and 1, 7. In a similar manner you can calculate delta 3. So delta 3 becomes like, what was the value of delta 1? So delta is given as 0.01, and delta 1 is delta by 2, so 0.01 by 2, and after that like we keep on multiplying by 1/2, 1/2, so we do it twice. So delta 3 will become 0.01 upon 2 raised to power 3, right? So once you have those values, you simply need to plug those values in this formula and you'll get the answer. But like the thing is, like they have asked two questions here, not just like what is the number of samples in the third round, but also the total number of rounds required to identify the epsilon delta optimal arm. So first, like let's solve this one. So it will be, so let's send again the 2 to the numerator. So 2, and we have this square. So it will be 3 raised to power 4. Again, this goes to numerator, 2 raised to power 14, and into ln of 3 will be there, and this will become 0.01 into 8. So after solving, like you'll get something around 3 to, so this is like multiplied. 32768 upon so power 4 ln of, again this 100 goes above, so it becomes 2400. So when you solve this, you'll get around 404.54, right? And this is like this first term, and this second term will be 7.78. And when you multiply, it will be 3148.6. But again, like same point, that this is for one arm. So we need to multiply. So should we like simply multiply by 64? The question I'm asking is, should we multiply by 64? You can write yes or no in chat. Someone wrote yes. But one thing you need to remember is like in this median elimination algorithm, after every round, we are eliminating some of the rounds, right? So even though like we started initially with 64 arms, how many it was? 64, right? So like at the end of round one, we will eliminate 32. So it will be 32. And then at the end of second round, we will eliminate more 16. So it will be 16 rounds remaining, right? In the third round. So we will be multiplying by 16. So this is another mistake which many students make. So you have to multiply by 16, not by 64, because the number of arms is also decreasing every round. So this is the key point here. And once you like do this calculation, it will come out to be 50384. But again, like for 50384, we have two options, either six rounds or seven. Like what is the total number of rounds required to identify the epsilon delta optimal arm? So like we had 64 rounds initially. At the end of first round, we had like at the end of first round, we eliminated 32. So we are remaining with 32. Then second round, it will become 16. Third round, it will become 8. Fourth round, it will become 4. Fifth round, it will become 2. And at the end of sixth round, it will become only 1. So only one arm will be remaining. So we don't need to go to seventh round, right? Because at the end of sixth round, only one arm is remaining. That must be the optimal arm, like epsilon optimal arm. So the correct answer here is option A. Now the ninth question. Consider a banded problem in which there is a single optimal arm A star. So there is only one optimal arm. There can be many in some problems, but in this problem, there is only one optimal arm. And again, this question is dealing with median elimination algorithm. Is it possible? So there are two questions asked and you have to answer those. So is it possible that arm A star is eliminated in the first round itself? Like in the first round, suppose if we have 64 arms like before, and out of the 64, one arm is optimal arm. So 32 are above the median and 32 are below the median. So is it possible that like the optimal arm can get eliminated in the first round itself? Like if it falls, like we are working in an empirical manner. So it is possible with some probability that it might land in this zone also. So if it's in like below the median, then it will get eliminated. So the answer is yes, it can get eliminated. So this is not possible. So in case it's possible, if it's possible, does this mean that the algorithm cannot output an arm that is epsilon close to A star? Like basically, like what was the reason we are doing this spec optimality thing? We are doing it because we want some algorithm which is epsilon delta spec optimal. So which basically means that with some probability, like we should be able to output this epsilon close arm. Although like it might be possible that we might not be able to output the epsilon close arm, but with high probability, like 1 minus delta probability, we are guaranteed to output the epsilon close arm. With small delta probability, like we might output a non-epsilon close arm. So like let's see in this question, like this delta was quite small, 0.01. So with 0.99 probability, we are like kind of guaranteed to output the epsilon close arm. So does that mean it cannot output? So again, like no, it doesn't mean that. So the answer here is also B. Well, check the chat once before moving to the last question. Okay, so like this is the last question of this problem solving section, and after this, like we will move to code. So we know that there is exploration, exploitation dilemma in RL problems, and consider. So this question is like related to Thompson sampling, and which step of the algorithm ensures that we perform exploration? So which step is it? Like, is it the initialization of arms, reward distribution? So initialization doesn't help in exploration, right? Updating the reward distribution based on observing actual reward for an arm. So this is like kind of, we are simply updating the Q value estimates, like the distribution. So in Thompson sampling, we maintain reward estimates of each of the arm reward distributions, and then we see like we sample from these distributions. So this updating, like, it's not ensuring exploration. Sampling the expected payoff of each arm from the corresponding reward distribution. So will this like ensure this that exploration happens? So maybe I'll give you an example. Suppose the right. So these are two reward distributions. So if this arm like has the highest Q value at current estimate, suppose this is the arm A, this is the reward distribution of arm A, and this is the current estimate of arm B. So although like you can see that the mean of arm A is much greater than that of arm B, but it is still possible that when we sample from this distribution, if arm B is very lucky, it can get sampled here. And if arm A is extremely unlucky, it might get sampled here. So in that case, we might pull the arm which had like less Q value estimate. So this kind of ensures exploration, even though like the Q value estimate, like the expected Q value estimate of arm B was smaller, but there is a possibility that it might get sampled. So this step ensures exploration. So sampling the expected payoff of each arm from the corresponding reward distribution. Fourth option says that identifying the correct arm given the set of expected payoffs. So correct arm, so this is basically exploitation step, right? This has nothing to do with exploration. So now like I'll move to demo. So before moving to demo, like I hope like there are no more doubts. If there is any doubt in any of the question in problem solving assignment, then you can ask me. I'll wait a couple of minutes. Like there is no more doubt. So I'll move to demo part. So this demo is built on the demo. So I'll start sharing now. Can someone confirm that? Are you able to see the code? Maybe write in chat. Okay, so you guys are able to see the code. So the problem remains the same. So maybe I'll open a Jamboard. So we have 3 coins. And these are not unbiased coins. So in unbiased coins, like the probability of head equals to probability of tail equal to 0.5. But this need not necessarily hold for these 2 coins. They might have like probability of head 0.4 and probability of tail might be 0.6. So these are not necessarily unbiased coins. These can be biased. Now the goal, so in this game, what happens if you get head, you get a reward of 1. If you get tail, then you get reward of 0. So the goal of the game is to like maximize the number of heads. Maximize number of heads. So again, like we played this game last week also. So at that time, what we were doing is we were simply using our intuition to get an idea about exploration and exploitation. So we did this in that way. And eventually, like we also noticed that we incurred our regret, some regret with this. So now, like I'll show in this week, like what happens if we don't care about exploration and exploitation and simply we become greedy with respect to the mean reward, basically the Q value estimate. So, like the UCV estimate, like UCV value, like it comprises of two terms. First term is the Q value estimate and second term is the confidence bound. So if we are greedy with respect to only the first term, then what happens is, like we will see in this. So we'll run this. So here, like we have 3 coins and we will be doing 20 tosses. Initially, like the mean values of all the 3 coins are 0. And let's maybe try coin 1. Now, once we have tried coin 1, like the mean value of it gave head and the mean value became 1. And for other 2 coins, it's still 0. If we are being greedy with respect to this coin 1, then we will like simply with respect to the mean value, then we will simply keep on pulling this coin 1. We like toss this coin 1 again, like then it becomes 0.5 because it gave a tail. But the point to consider is that this mean value of this coin 1 will always be greater than the mean values of the other 2 coins. So basically, like we won't be exploring anything in this case. We will simply be keep on exploiting with the coin 1. So this is why like exploitation is important. So let's see like what happens if we simply keep on exploiting this coin 1. 12 tosses are still left. And it is kind of giving heads less and tails more. So maybe like coin 2 and coin 3 were better coin, but since we decided that we will only exploit, we are being greedy with respect to just the Q value estimates, not focusing on exploring the other coins. Then like we are kind of moving in the wrong direction. Let's sample more times. So like there are 2 more tosses left. So again, like we can see that at the end, like we got like 7 heads from coin 1. But maybe like who knows, like coin 2 and coin 3 were the better coins. But since we decided to be greedy with respect to coin 1, we never explored coin 2 and coin 3. Now instead of like depending on the just the first term of the UCV value, what if we include confidence bound also? Now let's see what happens with UCV. So I hope like the first part is clear. I'll see chat once. Okay. So this is with respect to UCV. Let's see what UCV does is. So UCV has, I have explained this before also, UCV has an inherent mechanism of exploration and exploitation. So that term confidence bound, like even if some arm doesn't get sampled, that bound keeps on increasing due to that ln in numerator. So like even though some arm, like in our previous case, the other 2 coins, like I'll keep repeating these arms and coins repeat like exchangeably because like bandits are related to arms. So I'm using coin. You can understand that. So, but UCB will ensure that like these coin 2 and coin 3 get pulled. So in UCB, we basically pull the arm which has the highest UCB value. So let's see like what happens with UCB. So I'll run this. So I'll be sharing these code files with you. So I'm running for 20 processes. You can run for maybe 100 and see what happened. So initially, like our UCB values are not defined because we haven't pulled any of the arm. Now maybe let's pull. So in UCB, one thing to consider is that we pull each arm at least once initially. So let's do that first. We pull arm one. We don't care about the UCB value. We pull arm two, and now we pull arm three. So all the three arms have been pulled once. And the first two arms, like they gave head, and second, like the last arm, third arm, it gave tail. So we have like two arms, like with the same UCB value. So maybe like let's pull two. See, we pulled two. It gave head, both heads, but still like the bound of coin one became bigger due to that confidence bound. So due to that UCB values is growing. So like this means basically means that coin one hasn't been explored much. So let's explore it. So in this way, like UCB ensures exploration. So when we pull arm one, like basically toss the coin one, then again like both of them have heads now. So their UCB values are also same. So let's see, like we gave advantage to coin two. Now again, even though coin two again gave three heads, but like the coin one's UCB value is more. So we have to explore coin one more. So again, it's like both of these arms have three heads each, so their like UCB values are also same. But one thing you can notice is that even though like coin three we have pulled like only once, and it gave tail on the first attempt itself. So like it's still like this UCB value is increasing slightly with that Allen term. So it was 1.89, even though we haven't pulled coin three, but still it increased to 1.97. So there will come a point where like this coin three, if we don't select it, and it will automatically have such a high UCB value that we have to select it. So in this way, like exploration is ensured. So as of now, like we can go with coin two. So again, like coin two, we can see now coin one became highest UCB value. So sample coin one. So now it gave tail and its UCB value reduced drastically. This happened because of that Q value estimate, because now this tail is there. So initially it was 1, now it became 0.75. But now you can see that coin 3 has the highest UCB value. So now like we are kind of, even though it gave tail on the first attempt, if we were following like the exploration exploitation thing which we did in last lecture, then we would probably have not sampled this coin 3. But UCB ensures that you have to explore the coin 3. And I'm telling you this, like I have set the probabilities of all three coins. So like coin 3 is actually the best arm, but it got unlucky that it gave tail on the first attempt. So UCB is ensuring that we actually sample, explore all the arms. So now it's time to explore coin 3. So it gave head. But now coin 2 has the highest UCB value, so we sample coin 2. Now again coin 3. Even like coin 2 has given 5 heads. Still like UCB is ensuring that we need to explore coin 3. So let's explore coin 3. So now we have to explore coin 2 again. So how many tosses are left? 7. So again, like coin 3 has the highest UCB value. Now coin 2. Now there is a tie. Maybe we will go in favor of 3. Now like see, we gave the advantage to coin 3, and the UCB algorithm itself pointed out that you need to explore coin 1. So this is the beauty of UCB algorithm. So we sampled coin 1, but it gave a tail. So due to this, its Q value estimate reduced drastically. It became zero point 0.6. So now we have to sample coin 2. Now again, like even like coin 2 is has given a lot of heads, but still UCB is enforcing that we explore coin 3. It has kind of figured out that maybe point 3 there is potential. So now point 2 again. So I think we have done the 20 tosses, and we can see now out of 20 tosses, we got 17 heads, which is massive, right? It's almost 85%. So like we saw in like it's like 17, right? 17 out of 20. And in the previous example, when we were being greedy, we got like only 7 heads. And in the question which we did like last time, again here also we got 7 because we were using our intuition to judge which coin to explore. So this is the beauty of UCB algorithm. Like it kind of balances exploration and exploitation implicitly, and this results in a better reward. So this is for just for 20 tosses. So I'll be sharing this notebook with you. You can run for maybe a large number of tosses and see how UCB works actually. And in this demo, like I have shown UCB, but for Thompson sampling or median elimination and naive pack, like you can start coding in a similar manner. Basically, like in these lectures, we are not asked to discuss codes and all. These are mainly for problem solving, but I'm explaining this code because like it's good to see visually like how this thing happens. I hope like you guys understood it. So maybe I'll check chat once. So yeah, so a lot of people like they are finding it useful. So I'll be sharing this now. Like let's move to our next segment, which is the assignment 2. So if there is any query, then you can ask me regarding this code. Otherwise, like I'll be sharing the slides again. Okay, so I hope like the slides are visible now. Can someone confirm in the chat? Yes, so slides are visible now. So let's see. So in this section, like I won't be giving you exact answers, but since the deadline is tomorrow for this assignment too, so like every week, like we have our session on Tuesday, right? And your deadline of assignment will be Wednesday. Like for first week, it was like slightly loose, but from now onwards, you will have the deadline on Wednesdays. So we will be having our session like one day before Wednesday. So maybe you can attend like till that time you can make an honest attempt to solve the assignment. If you cannot solve it, then you can attend the session and maybe you are getting extra Wednesday to solve it yourself. So in this section, like again, like I won't be sharing the exact answers, but I'll be guiding you towards the answer. So let's start. So this question says that which of the following statements is not true about the Thompson sampling or posterior sampling. So Thompson sampling is also called posterior sampling because like we are based on the prior, we are updating the posterior again and again. So the point is like not true statement. We have to mention the false statement. So after each sample is drawn, the Q star distribution for that sampled arm is updated to be closer to the true distribution. Like this is true, right? Because like as we draw more and more samples, we like become closer and closer to the true distribution. You know, like Hovden inequality. So in Hovden inequality, it's like 2. There is a component of epsilon square and there is not 2, it's 3. And there is one more component of this number of samples. So number of samples, if we keep on increasing, like this thing, due to this negative sign, it will become small and small. So that probability that we are deviating will become small. Once that probability of deviating becomes small, then we are getting closer and closer to the actual true distribution. So this is true, this is not false. Thompson sampling has been shown to generally give better regret bounds than UCB. So if like nothing is mentioned, then by default you can take it to be UCB1. So yeah, like this is a fact, established fact that Thompson sampling generally gives better regret bounds than UCB. So there is a bound which is given by Lai and Lawrence. So Thompson sampling exactly matches this bounds to to even the constants in the bound. UCB doesn't match the constants. UCB is like in order of it matches the order, but this Thompson sampling and there is one more algorithm called KLUCB. It matches to the constant level, so it exactly matches the regret bound. So this is true statement, right? We have to mention the not true. In Thompson sampling, we do not need to eliminate arms each round to get good sample complexity. So elimination of arms like we do in median elimination, right? Not in Thompson sampling. So it happens implicitly, but we don't have to do it explicitly. So basically in Thompson sampling, what happens is like if there is some poor arm, then the distribution like will become closer and closer to the true. Suppose if some arm is here and some arm is here. So as we get like draw more and more samples, like this will like our maybe estimated one is this. So it will become closer and closer to the true one. And once it becomes closer to the true one, we don't need to like eliminate the arms. It implicitly does this. So this is also, we do not need to eliminate arms. So the algorithm requires that we have Gaussian priors to represent distributions over Q star value of each arm. It need not be Gaussian prior, right? We can have uniform prior also. We can have beta prior also. So it need not be Gaussian. So this is the statement which is not true. Okay, so like I gave the answer, but either way, like you can figure it out. So I hope like there is no doubt in this question, right? I'll check the chat once because these are important. These will actually be used to give you the certificate at the end. Assignments. Practice assignments are just for practice. These assignments are the real deal. So now, like, I'll check once if there is any doubt. There is no doubt. So now I'll move to question number 2. So question number 2 says that in UCV, the term, like, yeah, this term is added to each arm's Q value, and the arm with the highest value of this sum is chosen, right? Which one of the following would definitely happen? Definitely means always happen to the frequency of picking suboptimal arms. Okay. If we use like instead of nj in denominator, we are using nj square. So what will happen? Will it be like suboptimal arms would be chosen more frequently? Suboptimal arms would be chosen less frequently, or no change in the frequency of suboptimal arms? Or last one is suboptimal arms could be chosen less or more frequently depending on the samples. So basically, I'll explain like what is happening with this term. So this is the confidence bound, right? So confident basically as we sample the arms more and more. So if we have nj square instead of nj, so it will converge faster, right? But once it converges faster, then we might not have explored enough, right? So I have shown in code also how this term in denominator like this combined term ensures exploration and exploitation. So if we are like converging it quite fast, and it might happen that we might not have explored enough and we might end up picking suboptimal arms. But the key term here is would definitely happen. Might happen, right? Might not. Like basically it depends on the data, which like we don't know. Everything is stochastic here. Like with certain probability, things are possible, right? So I hope like you get the answer. So there's nothing definite here. I hope that should give you the answer. Well, check chat once. Okay. So now we move to question number 3. So this is again related to proof of UCV theorem. In fact, I'll tell you that in last week's lecture, this proof of UCV theorem is like quite important. And like you need to like actually derive this proof once by yourself. In fact, there is a question later which will force you to derive it yourself either way, but you should at least try to derive it on your own once, because this will be really helpful not just in your exams but in your learning also. Because these analysis tools of like proofs and all, like they are universal. They are not just restricted to reinforcement learning. You might be using them in some other courses also, or even when you are writing papers, you might have to perform some kind of analysis on some algorithm you might have invented or maybe proposed. So in the proof of UCB algorithm, like this is the L, they have given some L, and when this L takes this value, right, this term becomes zero. So if you have watched the proof of UCB algorithm, there were like eventually we got to the point where there were two conditions, right? And this condition, third one, corresponded to the case that when we are within the bounds, but still like there is some chance of making mistake. So this is that condition. But if we use the value of L to be greater than or equal to this number, then this thing reduced to zero, right? And we discarded that case. This is what happened in the proof. This is like for quick revision. So which of the following correctly explains being less than zero? So for greater L greater than or equal to zero, like this is definitely zero. But what happens if L, like how do we get this thing, like this entire entity to be less than zero? So first condition is definitely there, that this Ti of Si should be lesser than L, right? Because like this is for L, like if we take this value, if we take TISI to be equal to L, which is equal to this value exactly, then it will be zero. We need to consider the case where like this will be lesser than zero, and this can only happen when like we are less than this L. So this is definitely there. So maybe like we can eliminate this one. This is not possible. Now, like based on this condition, like there is a thus. So you need to like kind of derive another condition, right? So what is this? This is basically the concentration one, right? And where does this term appear in? So maybe I'll write it. So C ml equals to 2 ln of m by 10. So this is what it represents. That we have like the number of arms that have been pulled is m times. So this is like the total number of times we have pulled any arm. And L is the number of times we have pulled some specific arm. So like basically like this term TISI, like this represents the number of times we have pulled arm I till this time period. So this will go in denominator, right? So you can get an idea from here, like if like this is lesser than then 1 upon L will be lesser than 1 upon TISI, and similarly like you can add other terms and construct some kind of thing and see like how this, or is it this or is it this. So you need to see this. So like I think that is enough intuition for this. uh like this condition would definitely be there, and on the basis of this condition you need to check the condition on this and this. So basically like you need to get the answer yourself. So I hope like there is no doubt in this. If there is any doubt, you can point it in the chat or maybe unmute and ask me. But I feel like there are less people today, maybe like because this session is close to the deadline. And either way, like a lot of people will be watching the recording. So let's move to the fourth question. So fourth question says that which of the following is true about the median elimination algorithm? So again, like these are single option correct. Like can be only one of the options. So is it a regret minimizing algorithm? like median elimination. Like we studied it under the, like there was one algorithm called naive algorithm, NPAD, okay, and there was median elimination. And both of them were under the PEC framework, right? They were not in regret of minimizing. Regret minimizing was like UCV and its variants. Although like the professor hasn't discussed this variants, but they are there in literature. Maybe one I would honestly recommend is scale UCV. So you can read about the scale UCV. Now, so they have asked, is it true? Like, so it is not a regret minimizing algorithm. That is for sure. It's actually a PEC. The probability of epsilon L optimal arms of round L being eliminated is less than delta L for the round. So this they have asked for each round. Like, does this hold? I think like if you have watched a median elimination lecture and you would know like that we ensure this entity, like right? That the probability of epsilon L optimal arms at every round L, we ensure this. That the probability that all the like optimal arms get eliminated is less than delta L to that round. It is guaranteed, like, is it guaranteed? Like, we are in stochastic framework, like, it's not guaranteed to give an epsilon optimal arm at the end, like, with some probability it can give, and that probability is 1 minus delta. But with delta probability, like, it's still possible that we give non-epsilon optimal arm, right? Replacing epsilon with epsilon by 2, like, doubles the sample complexity. So does this happen? So the sample complexity of median elimination algorithm, what is it? Order of k upon epsilon square into log of 1 upon del. So if we like replace this by epsilon by 2, will it like double or like, actually it will become 4 times, right? So I hope like this will guide you towards the answer. So now we move to fifth question. Again, like we need 8 rounds of median elimination algorithm to get a pack optimal now. Approximately how many samples would have been required using the naive? So this question is like kind of convergence of two different algorithms. So from like one algorithm, you will get some value of a variable and then you will use it in this second one. So basically like it said, like how many rounds are there in the median elimination algorithm, right? So this is on base 2. Like suppose if we take like there were suppose k arms were there, and this is the like number of arms. And median elimination. So you can like figure this out. Just take the exponent on both sides and it will be 2 raised to power 8, which is 256 arms. So you will have 256 arms in this problem. So the first statement basically it's used to get this number, that the number of arms k is equals to 256 in this question. Now you'll have to use this k in this naive epsilon pack algorithm. So basically like how many samples would have been required using the naive pack algorithm, and they have given the value of 1 by 2, epsilon also is 1 by 2 and delta is 1 by 8. So basically like you'll have to perform the calculation again and see like what happened. So again like you need to remember some things that this like once you will be calculating for one arm, right? And you need to multiply by this. Don't forget this. So also like choose the value closest to the correct answer. So this is like kind of you need not do it very strictly. You can use some approximation, but try to do it like strictly and then see like which value is the closest. So this is the basic idea in this. So you just have to perform the calculation. So maybe like I'll write the formula 2k upon, so like generally this k is not there. I have included it because either way, like you'll have to multiply by this k and ln of 2k by delta. So this is for naive. Like although like we have derived the k from median elimination, but the second part asks for the naive back algorithm. So you'll use this one. And just you have the value of epsilon, you have the value of delta, you have the value of k. You just have to calculate it and see which value is the closest. So I hope like everyone can do that. So if there is any doubt, maybe you can write in chat or unmute. Okay, so there is no doubt. So next I'll be moving to question number 6. Question number 6 says that in case of UCV, the regret is generally of form like some function of n plus c. Therefore, the like if we have the confidence, this is the confidence bound of UCV1 to ln n upon number of times arm j has been sampled, and this function of n is this value. So this is basically the bound, and c has been given to be this, right? So what is the form of Fn for the confidence bound given by? So instead of like in UCV1, we were having this confidence bound to ln n upon nj. What if this 2 wasn't 2? It was some alpha, which is greater than equal to 2. So basically, like in this question, like this is the question I was talking about previously, like this question will actually force you to derive the UCB theorem again with some general alpha. It can be 2 also, but you need to derive the whole derivation and see what happens if you have this kind of confidence bound. Instead of 2, there is alpha. So basically, I won't be giving any hint here, but like the main intuition is that you need to get the derivation, do it honestly with this alpha and see where the changes are. And one more thing, like the options are such that even if like you put alpha equal to 2, all will give the same. So if you put alpha here 2, it will again give 8. If you put alpha 2, it will give 8. Alpha here, it will give 8. And alpha here, 116 upon 2 also 8. So you cannot figure it out that way. You actually have to derive it with this general alpha. So I hope like it will be a good exercise for you guys also. Like it will help you in exams also. Like these derivations, like once you do by hand, they will stick in your mind for a longer time. Otherwise, like I don't know, like you might forget it maybe in 2-3 days. So now 7th question. In the naive epsilon delta pack algorithm, suppose we draw samples for each arms instead of okay. So this basically says is that in naive pack algorithm, if we go by the algorithm which has been taught to us in recorded lectures, like we were drawing each arm this many times, right? But now what they are saying is that instead of this, if we draw each arm like this many number of times, just the difference is in this 2 inside the ln term. So 2 upon epsilon square ln of ky delta. What happens then? So again, like in this question also, so basically like you'll have to derive. So this question 7 and 8, they are kind of forcing you to actually do the derivation, take pen and paper, write the equations and see where the changes happen. This will give you intuition also. Maybe in exam, they might replace this ky, maybe ky2 or 4k. You'll have to do that. So you cannot like apply intuition there. So, but if you practice for 2K, maybe you might develop some intuition that how things are getting affected. Maybe from there you can get the answer directly. So like the thing is you need to practice these two questions, 6 and 7 yourself. Just do the derivation. Just make the appropriate changes at places like where you were using 2K, you will put K and see how the changes happen and how the final answer gets influenced. So now we move to question number 8. Okay, so question number 8 says that this is regarding median elimination algorithm. Which of the following is a plausible update rule? Plausible means like possible, like kind of okay rule for epsilon L and delta L. Okay, so here they are giving like they are giving some slightly different. Like you have been taught that epsilon 1 is equals to epsilon by 4 in the algorithm which has been discussed in class, and delta 1 is equals to delta by 2, and even the multipliers are given here. So basically you have to choose the multiplier which actually which is plausible. Plausible in the sense which maintains the pack guarantees and all those things. So how to approach this? So one thing is that you just need to make sure of two things here, right? That the summation over L of epsilon L, this should be lesser than epsilon. This is condition one. Second condition is that the summation over L of delta L, this should be lesser than or equal to delta itself. So you need to check these two conditions. And let's see how to check these two conditions. So suppose maybe I'll do for this one. So epsilon 1 is epsilon by 3. Then we are multiplying it by, so this epsilon by 3 remains same, and we are multiplying by 3 by 4. Again, at the next step also, like we will keep on multiplying. Now it will become square and so on, right? Basically, and they are asking that this should be lesser than, like this is the condition which you need to follow. So basically we can eliminate epsilon. So just divide by epsilon on all the sides. So it will become 1 by 3 plus 1 by 3 into some number 3 by 4 plus 1 by 3 into some number square plus dot like less than equal to 1. So basically the thing is, like, you don't know how many times you need to perform this summation, right? So we need to do this till infinity and see, like we need to ensure that this happens even at very large value. So basically like we have to find the limit of this series at infinity. Now, can anyone in the chat mention like what does this series represent? It's a common series. It's taught in class 10th. Maybe I'll write it again. So the formulation is like this. Some number is there, then it's getting multiplied by r, and it's multiplied by r again, and in this way it's proceed. So what is this called? So can someone write in the chat? GP. Yeah. So this is GP, geometric progression. And like what happens with this GP is like, so basically like the sum of GP is a Rn minus 1 upon r minus 1. But here the point is you don't know, you are not given anything, right? How many rounds and all those things. You are not even given like the number of arms from which like you can determine the number of rounds. So you need to do it for a general L, and basically like you need to take care that this happens even at infinity, like because there are continuous banded problems also. So in continuous banded problems, like there are infinite number of arms. So the bandits which have been discussed in class are like finite bandits, but there are continuous bandits also, like in which, like suppose if we are having a steering wheel of the car, then how by how much angle we should steer, like that is a real number, right? So it's continuous. Although we can discretize it, but it's essentially continuous. So like the maybe 0 to 2 pi radians. So this is like infinite possibilities. There are infinite numbers between them. So these are like continuous banded kind of problems. So can anyone write in the chat what is the sum of an infinite GP? Like, does anyone remember the sum of an infinite GP? So someone wrote a upon 1 minus r. Yeah, like this is correct. but there is a condition also for this to hold, right? And that condition is R should be lesser than 1. So if R is lesser than 1, then the sum of infinite GP is A upon 1 minus R. And if R is like greater than 1, then it will move to infinity. Like it's kind of unbounded. So basically, like what you have to do in this question is like there is a GP given. So basically, for all the four, you have to see like where the sum of the series is actually lesser than equal to 1, and where like in whichever option it happens for both of these, then like you can say that that is the correct answer. Maybe it might be 2, 4, like you'll have to check it yourself. So maybe like I'll do one. So maybe I'll do in this only. So for the first one, like A is like our, this one is 1 by 3 upon 1 minus R. R is our 3 by 4. We are multiplying by 1 minus 3 by 4. So it basically becomes 4 minus 3 over 1, then 4 by 3. And is this like lesser than equal to 1? No. So I think you can rule out this option and this option because of certain condition, but you need to check like the other two options. So I hope like you'll do it like honestly. And so this is the key term, like these kind of series, like you are expected to know them like AP, GP, and some common series like expansions and all, like because they would be giving you hints in this. So you are expected to know all these prerequisites. So now we have question number 9. So question number 9 says, suppose we are facing a non-stationary bandit. So this was like mentioned in lecture 1 also, like week 1 lecture, that when we are dealing with non-stationary bandits, we cannot stop exploring. We need to continue exploring till learning is there. So we need to keep on exploring because like suppose if we stop exploring and start exploiting, and some environment change happens such that the optimal arms become suboptimal and some suboptimal arms becomes the optimal arms, then we will be like incurring a regret. So in that case, we need to always keep exploring with some constant epsilon, right? So we want to use posterior sampling. This is Thomson for picking the correct arm. So what is the likely change that needs to be done to the algorithm so that it can adapt to non-stationarity? So here the question is like what? So the Thomson sampling algorithm, which was discussed in class, was for stationary. Yes. The distributions, like true distributions or the arms, they were not changing with time. But here the thing is like this distribution itself, like suppose this was for army, this might change after some time. This was suppose at time t equals to 0. This is at t equals to 100, maybe. Like this distribution itself got changed, the true distribution. So like initially, like if we were trying to estimate this one, we estimated this and now it has become this. So we cannot be relying on this one. So we need to keep on exploring. So how to like incorporate that change in the Thomson sampling so that like we can address non-stationarity also. So this you have to think it through. Like this is a thinking question. Update the posterior rarely. Like can this be possible? Like if we update the posterior rarely, if we don't update the posterior, then we will be quite close to the initial estimates, right? And will this help in adapting to non-stationarity? I don't think so. Now, randomly shift the posterior drastically from time to time. So, like, will this work? Like, we have the posterior and we when like shifted not just like slightly but drastically. Like, suppose if it was initially here, we shift at the next step to maybe here. I don't think like how this will ensure exploration. This might actually like completely uh, destroy whatever like we are doing. So changing drastically won't help, right? One question is no changes required. So Is it possible that the Thompson sampling algorithm, which was discussed in class, can it like adapt to non-stationarity also? So basically, like we were dealing with stationary distributions, right? So those were fixed with time, and we were trying to get closer to them. So will the default Thompson sampling work? You'll have to think this. Now, third option is keep adding a slight noise to the posterior to prevent its variance from going down quickly. So what if like if we add some noise? So basically in the vanilla Thompson sampling, which has been discussed in class, like there was no noise component. So there was a true estimate and we were kind of get drawing more and more samples and trying to get as near as possible to the true distribution, right? If we add some noise to the posterior, so what was happening if we had drawn a large number of, so if we have drawn each arm a very large number of times, suppose maybe 10,000, then like the estimated distribution and the true distribution will be quite close to each other. But like, what if the environment changes? Like we need to be like this variance should not reduce very quickly, right? So keep adding a slight noise to the posterior to prevent this variance from going down quickly. So if variance goes down quickly, then it will saturate. So in non-stationarity, you like we want something that just keep on exploring, don't saturate at one point. So this was happening in Vendates also, right? In Vendates, what was happening is like if we decrease this epsilon value, so after some time it will become so small that we won't be exploring, we are simply exploiting. So this is basically like the variance has become very less, right? So we were like we couldn't use this epsilon decay in vended problems. So when non-stationarity is involved, we need to keep the epsilon constant so that we keep on exploring. So same thing like applies here also. So basically we don't want that it converges very quickly to the true distribution. It should be like, so maybe adding the noise will help, right? It will prevent the variance from reducing very quickly. So I hope like this will guide you through the answer. So now we are moving to the last question of the session. So this is in the median elimination method for epsilon delta pack performance. Before moving to this question, I'll see chat if there is some doubt. Okay, so there is no more doubt. So Harshit has mentioned it correctly, like it was GP, and the sum of infinite GP was indeed A upon 1 minus R, and the condition was R should be lesser than 1. Right. So in the median elimination method for this one, we claim that for every phase, the probability of, so there is some term A, some term B plus epsilon L should be greater than 1 minus delta L. And the SL is the set of arms remaining. So basically like what we were doing in median elimination. So we were kind of ensuring that the probability that all the arms like get eliminated, all the like epsilon closed arms get eliminated in that round is small. Like we were maintaining that. So basically like if you have done the proof of this median elimination method, you'll know like what these terms represent A and B. So here, like basically, like there have been given three options for A, three options of for B. You just have to mention like which of those are true, right? So basically, like we were ensuring kind of that if we were in Lth round, we don't want all the epsilon optimal arms to get eliminated. So that kind of probability was there. So you need to see this. Like if you have watched the median elimination lecture, you'll know like what the answers are. Like this doesn't need much explanation. So I hope everything is clear. So with this, like we have reached the end of the assignment section also. So I'll check chat once again if there is more doubts. So there
Sir,
is no doubt. Yeah, yeah.
sir, I have doubt related to week one, as I have mentioned previously also.
Right, right.
Uh,
So just I'll cover this reading material section and then
okay,
like we will take that up. So
okay,
the
okay.
reading material like for like it's usual like if you get time like you need to try to read this Saturn and Barter book and Although like it's not covered, these bandits and all are not covered in much detail. Still, like you can read like the chapter two. So chapter two also comprises some parts of week one. So essentially, like you can read the complete chapter now. And this is the paper like of finite time. This is the paper of UCB one. So these guys like propose. So you can I'll upload these slides. You can click on the link and it will direct you to the paper itself. And like in that paper, like the theorem one is the one which has been discussed in class. But there are more theorems after theorem one also. If you are interested, you'll have to read. But one thing to note is that the notation which has been used in the class is different from the notation which is used in the paper. So you'll have to make that mapping yourself. And the third reading material. So this like first one, you should definitely try to do this. It is optional. So the and this is like action elimination. So this is the median elimination paper, right? So again, like this is also optional, right? So I hope like if you get time, you can explore these, but this you should definitely try to read. So and I like remember someone mentioned in the beginning that uh, they want notes. So I'll see if like it's possible to share the notes, and in the maybe the next lecture I'll link this book also. But I think like if you search on internet certain Barto, it will maybe I'll show you just right now. I'll share the screen. So it's there on this CMU University, so you can simply like just download from here. So this is the like second edition, and there's a first edition also, but I would recommend you to find like read from this edition. And this is the like second chapter. So second chapter is mostly about multi-arm bandits, and like the first five sections were basically related to week one content, and afterwards you can read from for week two. But you can read this up UCB one and gradient bandit algorithm. These are something extra from like class. So you can read some applications also of these contextual bandits in advertisements. And after that, like real, like actual reinforcement learning will start from next week. Okay. So yeah, so now like we can take up the doubt of yours. So what is this YouTube video?
Sir, actually, this is a timestamp where I am having doubt.
So whose video is this? Is it mine
Sir,
or?
this is from. Sir, this is the NPTEL course video only.
Oh, okay, okay.
From week. Actually, I don't understand the formula which sir has written, so I am having doubt in that.
Okay, okay. Just a minute. So there are two links. Like, should I click on first one or second one?
Yes, yes, sir. To add 2 points, I am having doubt. You can open
Okay,
anyone.
okay.
Like
Just,
the last one is from lecture 5 of week 1, and the last link is from lecture
yeah, yeah,
4 of week 1.
yeah, yeah. So this is the part like where you are having doubt, right?
Yes, yes, yes. So when you
Okay.
open the first
So
link,
just a minute. I'll
so
copy this link in Mozilla. It opened in some other
okay,
browser.
sure, sir. Uh, so,
Okay.
sir, here the sir at last has written one formula, that is P A is equal to A star is equal to 1 minus epsilon plus epsilon by n.
Right, right.
So, so like how it is related to softmax and how we derive this particular formula for A is equal to A star.
So basically, like I'll explain in Jamboard what has happened here. So you remember in this algorithm, like it is like recommended that we sample. I'll like write just write it. So with epsilon, just a minute. With epsilon, like basically like we are drawing a random number between 0 and 1, and with epsilon probability like we are exploring,
Yes.
and with 1 minus epsilon like we are exploiting, right?
Yes. Yes.
So like how we do this is like this: we like sample and random number, and if it's less than epsilon then we explore, otherwise like we exploit, right? So
Yes.
what has happened in this 1 minus epsilon part, right? Like it is possible that we include the arm that is like already the best arm, right? We can explore the best arm in this also. Like
Okay.
like this is for exploitation. So basically like what we want is with 1 minus epsilon probability we should exploit, right?
Yes.
And with epsilon, this epsilon is distributed over all the n arms, right?
Yeah. So it
And
like becomes
it's
epsilon
yeah,
by n.
epsilon by one n for epsilon by n for each arm. So that
Yes. Yes.
that optimal arm, like you need to add this also, right? So this is the actual like probability with which you will be sampling the actual optimal arm, right? So this way it
Mm.
comes, right? I hope
So
you
like why
understood.
we are adding it like epsilon by n, like for optimality purposes we are adding
No,
that.
no, no, no. So this was basically to mention like the probability with which we will be drawing the kind of optimal arm, like optimal in the sense empirically. So
Okay.
like basically like one with 1 minus epsilon we are exploiting, but with
Mhm.
even with within this epsilon there is a chance that we might explore. So how this happens is like if we have done this exploration, like if we got a number lesser than epsilon in this random number, then we will be at uniformly at random we will be picking any arm, right? So if we will be
Okay.
picking any random arms, then there is 1 by n probability that like that the best arm also gets picked. So this epsilon by n also gets added.
Okay. Okay. So like as far as I understand, it means like 1 minus epsilon we exploited, and from that exploration we can explore like we have a chance epsilon by n to explore in that also.
Yeah, so the like basically the arm which we are exploiting, this we can explore with epsilon by n also. So this is the
But
total.
sir, like, but we have already exploited it, so why we should like explore it further for epsilon
No,
by
no,
n also?
this is not related to exploiting or explore. Suppose there are arm A, B, and C, right? So
Okay.
suppose this is the B arm is the best arm empirically according to Q value. So with 1 minus epsilon probability, either way, like we will definitely be picking B arm, but with epsilon by n, we can also pick this B arm, right? So here it will be epsilon by 3. So like this is basically the probability of picking the best arm till we have seen. So this is the total probability with
Okay.
which we can pull the best arm.
Okay. Okay. So like which formula is like more correct? The second one is more correct, right? I think so.
Yeah, so basically like this is quite small, right? Or when you
Yes.
are
Yes.
coding, you can explicitly like instead of doing it uniformly at random, you can exclude that best arm and sample from others. So that is not much of a big issue, right?
Okay. Okay. Like in practical purposes, like epsilon will add by n will not affect much of this term,
Yeah,
right?
yeah. But generally,
Oh,
like you can explore the best arm again. Essentially, you are doing exploitation in the name of exploration. Right?
okay. 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 Got it. Got it. And is it related to softmax anyway? Because sir has like
No, no.
told us.
This was purely for epsilon greedy.
Okay.
This is not related to softmax. So, does this address your second doubt also, or is it like different?
No, no, it was different. Actually, I was confused between relative and absolute guarantee. Like, if you open the second link,
Right, right,
so sir has written the formula for relative guarantee and then written the formula for absolute guarantee.
right, right. Just a minute. So where does this happen?
So at last, if you see, so this is the formula for absolute guarantee. But before that, like if you scroll somewhat back in time, the sir has written the formula for relative guarantee. So like I'm confused, like what is the difference between two, like semantically? So
Just a bit. You pointed out where he has mentioned this. Like, is it like the correct timestamp?
yeah, here only. The sir is writing one formula.
Okay. Maybe like he'll know.
Yeah, this is the formula.
Right.
So this sir has mentioned this is the formula for relative guarantee.
Right. And what is the formula for absolute guarantee? Where is it?
So like sir has rubbed it like after some time and written the formula for.
Okay. Okay. So I remember this. I think this was a mistake. Like he initially wrote something and then like made it correct.
Yeah.
So
Actually, I understood the absolute
yeah,
guarantee formula, but there is doubt like
yeah.
what is this relative guarantee?
So
Because
basically,
sir has
like
not talked.
you can kind of ignore it. Just like go with the absolute guarantee because that is what is actually used. So absolute
Okay.
and relative are like basically absolute is in absolute terms, relative is in with respect to some other terms. So you can make it absolute like suppose like percentages. Percentages are relative, but if you get the exact numbers themselves, so that is absolute. So he wrote in terms of absolute later. So I think like it's better you follow that one.
Okay. So can I confirm like the formula which I've written in my notes is like pack guarantee. That is basically probability of absolute terms of QA minus Q star A star is less than
Mhm.
epsilon is greater than equal to 1 minus delta.
Right.
So basically the probability should be greater than equal to 1 minus delta in other words.
Mhm.
Like it should be at least 1 minus delta in absolute
Mhm.
guarantee.
So delta is basically the mistake probability, and 1 minus delta with that probability you should be correct. Epsilon correct.
Yes. Okay.
Yeah.
Got it.
Okay.
Okay. Thank
So
you.
right, like I'll check in chat if someone else has a doubt. Otherwise, I'll be closing the session. If someone else has a doubt, like maybe you can just unmute yourself and ask. So, so if there is no more doubt, then like this is the last slide. Okay, then okay, then like I'm closing the session. I'll stop the recording now.